come back to the real numbers. Next lesson of it. Last time we had done about Euclid's division algorithm, and there we had done two type of problems. One to find the HCF, and another the numbers which can be written in the form of 2q plus 1 or something of this kind. Okay, now we are coming to the next topic. There are 2-3 topics which I am going to do today, and after the video I will be giving you the homework separately. The first one is condition for a rational number to have a terminating decimal expansion. This is in continuation with what we had done in the 9th standard. I'll give you some examples. See, all of you know that rational number can be expressed as a terminating decimal as well as non-terminating recurring decimal. Now here we have to see when it will be terminating and when it will not be terminating. Okay, the simple example let me take 13 by 10, which is equal to 1.3, terminating. I'll take 1 by 8. Okay, 1 by 8 is nothing but 0.125, terminating. Okay, then I will take 1 by 25 or 4 by 25, anything. Okay, 4 by 25. This is again a terminating, that is nothing but 0.14, then how much? 5, 25, 15, 100, 2. Check it, this again. Let me check it again. 4 by 25, it is again terminating. Now let me do some other examples, like 1 by 3. 1 by 3, when I see it is 0.333, non-terminating. If you take 1 by 7, it is also not terminating. We have done last time. Okay, it is non-terminating, but it is repeating. At the same time, some other example, 2 by 15, if I take, it is also a non-terminating decimal. Okay, so the thing is that now here it is terminating and here it is non-terminating. So let us observe here. Let us observe the denominators here. In this, the denominator is 10 and the prime factor is 2 and 5. Here the denominator is 8 and the factor is only 2. And the denominator is 25, the factors are 5. Whereas here the denominator is 3, 7, 3 and 5. So what you see, when the denominator is only 2 or only 5 or 2 and 5, that means the decimal expansion is terminating. Therefore, but one thing you have to remember, that you have to write it in the standard form. So if it is 15 by 24, okay, 15 by 24, where if I find the factor of 24, it will be 2 into 2 into 3 into 2, correct? 8 into 3. So here 3 is coming. So we feel that this is a non-terminating decimal. But this is not written in the standard form. So we have to first write it in the standard form. It will be nothing but equal to 5 by 8. And this can be written as 0.625. So here we see that it is terminating. So first thing, whenever it is written in a form of P by Q, we have to bring it in the lowest term, or we have to write it in the standard form. And after writing in the standard form, we have to find we have to see the denominator. If the denominator is in the form of 2 to the power m into 5 to the power n, when I say where m and n are non-negative integer, this m can be 0. If m is 2 to the power 0 into 5 to the power n, then it is terminating, because 2 to the power 0 is 1. So here we see it is 8, which is 2 to the power 3 into 5 to the power 0. So that is allowed. So m and n, where m and n are non-negative integers. This is the condition for the rational number to have a terminating decimal expansion. So if a rational number has a terminating decimal expansion, then the denominator of its standard form, remember here, if standard form, very important, has the prime factorization of the form 2 to the power m into 5 to the power n, where m and n are non-negative integers. So this is a concept which we have, which is just a continuation of the 9th standard which we have studied, but it may come for 1 mark. So in MCQ and all, the such questions come. Next I come to the next topic, and that is fundamental theorem of arithmetic. The name is big, fundamental theorem, but the concept is the same thing what you have learnt in lower classes. So fundamental theorem of arithmetic, here it says that every natural number other than 1, is expressed as a product of primes, and the expression is unique other than its order. What does it mean? See, if I take 24, okay, and 24 can be factorized, right? Yes, so 24 can be written as 2 to the power 3, 2 into 2 into 2 into 3. That means 24 can be expressed as a product of prime factors 2 and 3. Okay, so you take any number, any natural number, you will find that it can be expressed in the form of a product of prime, and it is unique. What do you mean by unique here? That means this 24 cannot be expressed as 7 into something or 5 into some other prime numbers. It will not be expressed. But the order you can change. 2 to the power 3 into 3 can be written as 3 into 2 to the power 3. That does not mind. Okay, so fundamental theorem of arithmetic states that this statement is important. You have to understand it and learn it. Every natural number other than 1 is expressed as a product of prime, and this expression is unique other than its order. Now what are we going to do is, we are going to learn how to find the HCF and LCM by using the fundamental theorem of arithmetic. I'll take two numbers. Let me take 24 and 36, simple number. So first we will find the factors. HCF and LCM both let us find. Okay, when you find the factors, just now we found 24 can be written as 2 to the power 3 into 3. 36. When you find the factor of 36, yes, you find that it is equal to 2 square into 3 square. Now how to find the HCF? This thing also you have done in the lower classes, but slightly you have to use the exponent here. So HCF is nothing but the common factor. Okay, here 2 square is there, here also 2 square is there. Okay, here 3 is there, here also 3 is there. So the common factor is 2 square and 3. So what we can say, the common one we have to write and the lowest exponent we have to write. 3 and 2, the lower exponent is 2, so it's 2 to the power 2. 3 and 3 square, the lower exponent is 1, so it is 1. So 4 into 3, 12 is the HCF. I repeat, to find the HCF by prime factorization method. Last time what we did by Euclid's method, that is different. Euclid's method is different from fundamental theorem. So we have to factorize it. That means we have to factorize it and write it in the product of primes. After writing it in the form of a product, we have to find HCF. For that, the common one we will take and the lower exponent we will take. Common one we will take, the lower exponent we will take. That will be HCF. Now let us find LCM. To find out LCM, the common one we will take and then you will write the the one which is a larger exponent, and here also 3 square. So this will be 8 into 6, 8 into 9, 72. So 72 will be the LCM and 12 will be the HCF. So let me take another example. Okay. Example 2, and here let me take 336 and 54. When I find the factors of 336, I find that it is 2 to the power 4 into 3 into 7, and 54 is nothing but 2 into 3 to the power 3. So to find HCF, what we will do? We'll take the common one and then the lower exponent we will take, that is 2. And here common 1, the lower exponent is 1. That, and the 7 is not there here, so it is not common. So 6 is the HCF of 336 and 54. To find LCM, we'll take the common one and we'll take the higher exponent 2 to the 4. 3 higher exponent. And 7, and here 7 is not there, that means it is 7 to the power 0. So there is no need of writing, but you come to know that 7 to the power 1 is the common one, the higher exponent. So what you can say for LCM, the common, the one which is not common also you have to write, and the one which is common, for that you have to take the higher exponent. And here when you multiply, you get this as 3024. So this is the way to find HCF and LCM by prime factorization method. I hope you understood. So it is the same thing what you have done in the lower classes. Instead of making a group like this, you will write it in the form of exponent and write the answer. Now the next concept, let me do that and then complete it, okay? And the next concept is a very important one. Very important in the sense 100% it comes in the board examination and all the examination, okay? So